Now, I would like to introduce Hung Yin, which is a postdoctoral student at KTH Royal Institute of Technology. He works in the Robotics Perception and Learning group. And Hung's work, I've known him for quite a while, works mainly in the intersection between robotics and machine learning. And to be more precise, he wants to improve learning-based robotics by incorporating these problem structures, such as task representations, dynamical systems, and optimization-based control. Okay. Hung is a dual PhD from EPFL and from Technical University of Lisbon. He was supervised by Professor Aude Billard, Professor Paiva and Professor Francisco Melo. And he has a master and bachelor's also in the Shanghai Jiao Tong University. And he also worked as a software engineer at Siemens. And it's a pleasure to have Hung Yin. And fun fact, he quite likes historical RPG games, which I know. And without further ado, Hung, please start your presentation wherever you're ready.
Thank you. So, okay, so I should share my screen. It over. So can you see it now, everyone? Is it good? I mean, the slides, can you see that? Or probably I should move this a little bit. Oops, I cannot hear you guys.
Yeah, it's perfect time. The slides are perfect.
Okay, okay. Oops, I'm popping up something, but I will leave you to handle that. Okay, thank you so much. Thanks for the kind introduction from Miguel. And hello, everyone. And today I'm going to give a talk mainly about the research has been happening at KTH RPL. Basically, it's surrounding the topics like how to exploit efficient representations to boost the performance of learning-based robotics. And specifically, I will highlight some kind of applications and the progresses on the topics of visual planning and context-rich tasks. Okay. So the motivation of this line of research is like introduced by Miguel to enable the robots to learn efficiently. So we have witnessed many progresses from the advancement in deep neural networks that allows us to build some kind of end-to-end policies from raw sensory input and to like the raw control signal like the torques. So one of the questions is that how can we make this universal models to learn even more efficiently, because it is well known that this kind of a deep learning paradigm is a kind of data hungry. And this is specifically true for different modules within a robotic system. So imagine you may take a picture of a clothes and you can represent the configuration of a clothes in the format of the raw pixels. And on the other hand, you can also represent it with some kind of the contour of the shape, and which means that you somehow ignore some kind of irrelevant features like the wrinkles, like the illuminations. And this can be used as a more effective representation for your learning algorithms. And the same case can be applied to actually the action perspective, means that, well, on one hand, we can just to output, have a policy to output the control torques, while on the other hand, we can consider the actions at the level of trajectories. So the talk for today, I'm going to touch both of these two perspectives. And the first one is about the state representation. Basically, I will show that how such kind of representation can be learned by exploiting some kind of a structured cost when you are extracting some the latent space. And I will demonstrate especially for the application of how this can facilitate planning the manipulation for deformable object like clothes folding. And also for the second part, I will talk about the action representation, and specifically this will somehow incorporate some results from the traditional control literature. And we can demonstrate that we can achieve some kind of stable reinforcement learning to address some kind of quite challenging context-rich tasks. So the first part is mostly built upon our recent publication at IROS, and which is the main work done by 3 PhD students, and one of them is the visitor from Italy, and also they are supervised by the professors from the 2 universities. So the idea of this work is trying to address some kind of planning tasks. It's a little bit beyond what the traditionally dealing with in the motion planning, which mostly handled a discrete state representation. So here specifically, we are interested to handle the state or say the observations that are high dimensional. So this can be like kind of you take a picture of a stack of boxes, then that means that probably the underlying, although the observation is high dimensional, but the underlying states representation could be a finite dimension, like probably like in the position of the blocks. And also there's a step further from that, you can think about we are observing the configuration of a deformable object where you might say that the inherent dimension is infinite. So how to address this kind of high dimensional problem? A very, straightforward way is trying to do some dimension reduction. You can use PCA, or most recently, you can use some kind of a deep generative models, such as variational autoencoders. So basically, the idea is that we try to learn two types of the two loss terms. One term is trying to reconstruct the high dimension representation, and the other part is somehow some regularization at the low dimension, a more compact representation as the bottleneck. So after learning such kind of representation, you obtain some kind of encoder. We can project the observations from the original space to this more compact space, and then hopefully you can efficiently perform planning in this embedding space. So is this provide us sufficient or satisfactory performance? Well, not really. I mean, a lot of generative models will show that they somehow learn space that are meaningful with some kind of semantic structure by doing this kind of linear interpolations, and to show that all of this intermediate point can be reconstructed with some kind of phase that are still, looks believable, like with different orientation or different visual expressions. But more recent work demonstrated that actually you can never guarantee that this learned space can have some kind of well-behaved, let's say, a metric, a global Euclidean matrix. So that means, put that in the context in our case, is that that means that when you try to traverse on this kind of a manifold, you may end up with some kind of state which is invalid from the task perspective. So so the question is that then how we can learn a space with a better structure, and this means that we want a representation can somehow emphasize that the part that are relevant to task and ignore that the task irrelevant features. So in this case, it could be like we want to encode the configuration of the clothes that matters and that are significantly different from the folding task perspective. Like that, I can put my right arm to one of the corner of my clothes, and this should be regarded as significantly different from the one where the clothes is flattened in the initial pose. And also, on the other hand, we want to say that we want to ignore some kind of the details that are not important, like you may have some kind of different wrinkles or different way of twisting your hand, but from the task perspective, we can regard these two observations are more similar. So we want these two encodings to be close to each other in the latent space. So how can we reflect such kind of structure? So the idea here is that we can leverage the action labels, that we have the data set for each data instance. You have these two pictures. One is the source one, and then the other one is like kind of the due to some kind of action, you got some kind of a causality here. And so the third part is indicate if there's an action exists or not. So if there's an action there, then you might also attach some kind of extra information, like where you are grasping and where you are releasing the clothes. So you have this kind of a causal relations between these two images. Or the other one is like that the action is not task significant. It could be some kind of a random noise. So you believe that these pairs of the images are supposed to be treated as equivalent. So with such kind of idea, we can train variant of variation autoencoders. So basically you have two of the lossless functions which are equivalent, which are just reflecting the traditional VAE, and then you have this third term that are reflecting what we just mentioned. So basically you want, you want the latent encodings of the pictures that are caused by an action to be significantly, to be at least larger than certain, at least larger than some kind of threshold. And if there is not an action, if it's not caused by an action, you want to say that, okay, it should be treated as close as possible. So this additional term can reflect that what's the structure we want to impose in this latent space. And after we obtain this kind of latent space, we are proposing to build a roadmap on top of that. Basically, it means that you try to encode in your entire data set, and you start to create the edges to connect the state can be transited due to the actions. And by doing so, and you can have this kind of a roadmap to better capture the structure. And I mean the global structure, or say the global dynamics, how this kind of a task are evolving in this embedding space. So concretely, this can be done by 3 steps. First, like I say, that you just basically do the encodings for each of the data point, and then you also establish the links. And then in the second phase, you start to do some kind of clustering. So because of that cost, you can somehow encourage to build some kind of cluster for the states that are similar to each other. Then you can build some kind of a centroid. And then in the third part, you start to label each of the centroid, each of the cluster, and then also merge the links and to be, so you just assume there is a transition between this kind of local, this local area or the local partition of your space. So this will, the roadmap will give you like kind of a path of the observations that make sense from the task perspective, but it didn't really tell you how to execute from the one observation to the other. So to address this, we're also proposing to learn a separate so-called action proposal network. It's basically you put the input of 2 adjacent images, and it can somehow predict you that where you should grasp and where you should release that. And by incorporating all of these kind of modules, you can see that if you give me a starter state and a goal state, I can first to get some kind of visual plan that are all of the like kind of the expected image I want to achieve, and then run this kind of APN to get the action plan. And to put that together, you end up with kind of a planning, executable plan for like kind of a vision-based tasks. So how this kind of the extra term helps us to do this, to have a better structured space. We are trying to demonstrate this from a kind of a toy example. So in this case, you have this kind of the underlying factor, and which is governed by the position of the blocks. So in this case, we want to show that how well we can start from a starting position and to the goal station. And by traversing on the LSR, you can see that all of the intermediate states, by decoding this intermediate state, you end up with something that very valid state that are not violating any physics laws, something like that. But if you are doing naive linear interpolation, you can easily see that, as what we mentioned before, that you can may go out of your task manifold, you end up with some kind of observations with some kind of ghost blocks there, which is actually unrealistic. So we also have some kind of numerical evaluations, and we see that without this enforced structure, and it didn't work very well. And also we run some ablation studies to see which metrics works best for our clustering process, and it ended up with the best performance for L1. But this is just a toy example. Yeah. So you can see that it's achieved something 100%, which is, yeah. And also we run this for our motivating tasks. So basically we have this kind of a robot to first run the visual planning. And because of the uncertainty about execution on the real robot, so we have to rerun that for each step. And so if this ends up something different from what you planned, so you can start to correct that. And we run a bunch of the rollouts and also show that L1 gives us the best performance. So this demonstrates how the entire Siemens system works. You have these starting images and the goal images, you both encoding them into the latent space. And you can run any kind of graph search algorithm or like sampling-based planning. And so you probably have multiple feasible passes. Like you can first make the fold from the right hand or make the fold from the left hand. They are equally equivalent. But so then you can start to choose one of them, one of the plan, and then you run the APNs to predict where it's supposed to graph and where it's have to go. And then, as we mentioned, you start to run the replan because the resulting images is probably not exactly what you are expecting, but that doesn't really matter because you can embed it into the latent space again, and then you get some kind of a shorter plan. Now you don't have much choices because you are not starting from the very beginning. So there's only one set of the images you can choose, and the same that you can exclude that one and to fulfill this step. And it's the same, and you can do this iteratively. You choose this, choose the bottom of the t-shirt and finish the folding. Yeah. So I'll give you a summary about this first part. Basically, we demonstrated that it benefited to learn some kind of state representation with a better structure, and we show that you can achieve this by leveraging some kind of primitive demonstrations, and we can highlight it can help us to achieve some kind of challenging manipulation task which involving high dimension or unstructured perception input. And we are open sourcing some other materials, so if you are interested, you can check from the link. Okay, and for the second part, I'm going to talk about a paper in submission to IEEE Raw, and which is collaborating with another PhD student at RPL, and also he is a supervisor at ABB Corporate Research. So in this work, we are trying to address the efficient reinforced learning problem, and we have seen that many success by training neural network policies which directly take the raw input like the joint positions and output the joint torque values. Some recent research has demonstrated that it's actually the learning efficiency can be improved if we try to learn instead of the torque, control torque directly, but try to learn the parameter of a variable impedance controller. So this gives us some kind of insight because you are no longer just try to predict a raw output, but some kind of a parameter of the parameter of a controller that are suitable for your task, specifically for context-rich tasks, because now you are treating the robot as a spring dumping system, so you can somehow implicitly, gracefully handle this external kind of a contact. So you don't have to directly specify what's the force, what's the desired force, what's the appropriate force you should apply to the environment. So we are asking some kind of research questions further from that one is that we show that, okay, you gain something by not learning from a task agnostic torque policy by learning some kind of impedance policy. But what if we have some kind of more feature to the policy we're treating, like such as the stability? And this is important because if we manage to learn a stable policy, we can somehow grant a certificate for our learning-based system. And this is could be important if we want to deploy such kind of system in the real world. And also another question is that since we are learning some kind of a special type of impedance controller, will this impact our learning efficiency? Because we are now learning from a more restrictive class of controllers. And the third problem is that how can we realize this kind of stable certificates? And actually many kind of research are conducting based on this model-based approach. Basically, you can learn this kind of dynamics from the data. But as we may know, the learning of the dynamics might be inaccurate, and especially this could be neutrally hard if we are dealing with contact-based data. the data collected from contact-based tasks. So, and for the impedance controller, we have some kind of well-known results date back to 1980s for fixed gains, but for the variable gains, only very recent, we got some kind of progress in the control community. So the idea to address all of this is trying to exploit the so-called emoji policy, and which is from Mohammed's paper in 2014. So the form of this policy is basically a combination of different spring dumping system. You have a global one, and you have a set of local ones which are activated by weights that depends on your state variable. Yeah. So in total, you have some kind of a state-dependent variable VSE policy. And this work shows that given some kind of stability conditions, most of them are like the semi-positive definite about the parameters, you can achieve a global stability in the free space. And if you are establishing some permanent contact, you can still achieve a passive system, and if your environment is not actively actuated. So our idea is to use this policy as the form that we are trying to learn from. So, and specifically, we want to take a step further. It's just not to trying to learn a target policy that is stable, but also for the exploration. So in that sense, we are doing that. So in that sense, we are trying to achieve the so-called old time stability. It means that both the target policy, which is deterministic, and the exploratory policies should be stable. So in that case, we supposed to explore, make the exploration not in the action space, but now in the parameter space. Because if your parameters are subject to this kind of constraints, you can be sure that all the actions you are sampling are also stable from the control perspective. Yeah. So the idea is that trying to learn together with this kind of a constraint, which is usually not very common in reinforcement learning. And we try to address this by using the cross entropy method, because basically this is, allows you to design different proposal distributions, and you take examples from this distribution, you evaluate them, you evaluate the return, and you use the return as the weight to somehow re-estimate the new proposal distribution, and then you try to iterate, you end up with a good distribution of your parameters. So in that case, we can construct this proposal distribution to account this kind of stability conditions. And since they are mostly concerning about the positive definiteness, and we specifically to choose a factor of this distribution as a Wishart distribution. So in that sense, you can somehow start to ignore this kind of stability after you adopt this specific form of distribution. So, and for the sampling, so this is easily resolved, but for the estimation part, this will be a bit more involved. That's because for the Gaussian, for the most commonly used Gaussian, you can have a closed form solution. But this is not the case for a Wishart distribution, especially both of the parameters are unknown. At least to our knowledge, we didn't really find a good way to do that. So we try to address that and to contribute an updated rule by looking at the empirical behavior of this kind of parameters. So basically you can see that one of the parameters is somehow in charge of the diversity of the samples, and the other one is gives you, we can observe some kind of closely to linear relations between the parameter and the entropy of the data. So but on top of that, we propose some kind of rules that update these two parameters by accounting for the reward and also like kind of the stability, not the stability, the convergence of the explorations. So we want to demonstrate whether this with the extra stability consideration, it can still learn well or not. And this I'm showing a case that you are trying to insert a block into, how to say that, a nut. And basically we can clearly see that ours policy form learns faster than the baseline, which is also outputting the parameters of a variable impedance controller, but without the stability guarantees. So this can highlight some kind of data efficiency, but we are not really advocating that, because now we are comparing two different learning algorithms. So one is based on the CM, the other is based on the PPO or TRPO. So it's hard, it's still not conclusive to say that it is because of the algorithm itself or because of the stability prior. But at least we can show that the introduction of the stability did not compromise the learning efficiency. I think this is something we can draw from this. And also we are trying to use that to address some kind of a challenging packing or task on real robot, because we observe some kind of a satisfying learning efficiency in the simulation, so we can deploy it on the real system. And according to our observation, that around like kind of 20 iterations, you can successfully make the insertion for most of the time. And yeah, and this is something that gives you some kind of a confidence. Such kind of system can be directly used on the real robot system for a real robot learn. And also we want to highlight some kind of advantage with this stability consideration. So if you are doing this kind of deep reinforcement on a robot, you might be familiar with some kind of crazy explorative things. And this will not happen in our case, because all of this kind of rollout from the sample, the sample, the parameters have this kind of tend to go to the regulation point. So you can see that from the statistics, especially in the early stage of the learning, our approach gives somehow will explore the space in a less aggressive manner. So this might hint some kind of benefit from the safety perspective. So the summary for the second part, and we answer all of this kind of identified challenge and the questions. And yes, we can learn we have a stable reinforcement learning, and even from that we have the all the time stability. And also we show that it didn't really compromise the learning efficiency, and potentially it can maybe have some kind of a benefit. And also we show that by adopting this specific form of the VIC policy, we can achieve a model-free stability guarantee. And also you need to have some kind of a smart design about the updated rule of your reinforcement learning algorithm. Yeah. So I think that's all for my presentation, and I would like to take your questions.
Okay, let us thank Hang for the presentation, please.
Am I within the time frame? Okay, sort of. Yeah.
So thank you very much, Hang, for the presentation. And now I open the session for questions. So if anyone in the chat has a question, please just raise your hand in the chat, or just unmute yourself if you can.
Can I go with a question, Miguel?
Yeah, sure. Go for it, please.
So thanks, Hang. Very cool presentation. Good to know what you've been working on lately. So I have a quick question on the first part of the work regarding the clothes. So I was wondering, like I would expect that once you use, for example, different kinds of clothes or clothes with different colors, that you may run into some problems with the latent space. I guess that the metric doesn't make much sense there. Have you thought about that problem? What problems do you foresee? Do you have any possible solution for that? So yeah, those would be my questions. Thank you.
Yeah, I think this is a very good question, because it touches another part of how general system could be. So here we are only showing that for one specific close, that no matter what configuration it is, I mean, you can basically cannot enumerate all of them. This kind of encoders can help you to project it into kind of a space. You can still reason about the path to connect each of the states. But for this kind, I mean, then it really depends on what the data representation you are using. You are feeding to this kind of variation autoencoders, right? I mean, so here is a kind of, you are dealing with the raw pixels. So you didn't really rule out the impact from like the textures, the colors, and even the size of of this thing. And so, yes, so this is indeed something that you can work along towards that, so you can have some kind of better representation that maybe you can exploit some kind of geometry similarities, and to also to generalize the plan you obtained for the demonstrated object. Yeah. But this is not achieved in the current system, because I mean, yeah.
Okay, so you're saying that you think just like maybe a more complex autoencoder would work? Because the first problem that comes to my mind is that during the visual planning, I'm thinking that maybe the autoencoder could potentially say that, okay, you start with this white piece of cloth, and now you move I forgot. You move part of the cloth to one side, and then suddenly the plan thinks it's a different color. The cloth would have a different color? Does that make sense? Or could that happen? Essentially, like the different steps of the plan start getting those clothes with different colors and messing up the textures and all that?
Actually, they have some kind of processing in the pipelines, because I mean, if you can see that from the data, you remember all of this kind of clothes has a black background,
Mm-hmm.
because that means that you somehow extract those kind of clothes. And,
okay.
Yeah, so somehow that is will not impacted by, I mean, the color, the area of the color in the background. It's that won't be impacted. I don't know if this is to your question.
I think I was asking something different. I was
Right.
thinking that, okay, let's say that now we want your system to work with different pieces of clothing with different colors, okay? And as far as I understood, your answer would be that we could start with a more complex and a better variational autoencoder to somehow represent better the clothes that we use. And I was wondering if during the planning, we could see things like weird things happening where we start, getting confused by the different pieces of clothing that we are representing with the autoencoder. Or is this even a valid question? That's what I'm trying to understand.
I think this question makes sense, and because I mean, here what you get is not the real state, right? You get it still like in the observation. Even for one specific type of clothes, this might be ambiguous. Say that you just don't know how this kind of arms are folded if you only look at it like in the folded state, right? So you don't have all of this kind of information. It definitely could be ambiguous. And but for the first part, I guess probably you don't need a more complex variation autoencoder. It's just what type of the data you are feeding to the variation autoencoder. So here, like in the kind of the pixels, you already rule out the background pixels. So somehow it can be robust to the different background colors. But if you want for more, like in the textures, maybe like what I mentioned that before, like probably you just need the you probably need some other representative like the contour of your shape. I mean, so but yeah, or maybe you need some kind of more complex generative model, because I mean, so you see this kind of reconstruction from the VAE is always give you some kind of blurry thing. So it's always a kind of a debatable thing that if this coding is good enough. But yeah, for certain kind of a task, like if the shape changes significantly, if you have some kind of feature can identify that easily, then it is fine.
Okay, thank you.
Okay, thank you. Kim, you have a question, so go for it.
Hi, Hang. It's nice to see your face and to hear about your research. So my question concerns the role that the human could play in this kind of learning problem. So basically, correct me if I'm wrong, but having a robot able to learn these representations by itself saves the designer the effort of having to think very hard about how to encode domain knowledge into these tasks, right? In the sense that we don't want, same with deep learning in general, we don't want the engineer to have to hard code specific features, specific representations for every problem. So I think that's a very powerful approach to these problems and potentially for knowledge transfer and generalization. Now, for these tasks that we know how to do, like I know as a human how to fold clothes, and I know what matters for folding clothes, or I know how to pick up blocks, for these specific tasks that we kind of already know how to do. Do you think that there is a hybrid kind of way where we could have a human in the loop in that representation learning process, where the human could somehow direct the robot in its learning? Or do you think that we're far from that? Because so far I'm guessing that the humans are providing maybe labels for your data. Are you working with human labeled data, or are you letting the robot kind of, yeah. So do you think that the human can be a little bit more involved into this process than just labeling data points?
Well, absolutely. I think there's always this kind of the argument along the two lines, which the traditional, you want to synthesize the entire system, and the other one you let the data to decide everything, to completely end the thing. So what we are here taking is some kind of the intermediate level, I should say. So if you have the knowledge to, I mean, if you, it's not that hard for you to incorporate this kind of knowledge, then why not do that? Because I mean, you have many research has shown that it's indeed benefit. But the question is that how easy it could be, and how to enforce that. Sometimes, like you say, that it's probably like kind of tedious for human to label each single of them. And I should mention for the first part, actually, you do have some kind of a human labels, because you are basically doing the demonstration of each of the primitives, like where to pick, and so if there's an action resulting from this image to this one, so but here is it really, I think I mean, my 2 cents is like then it depends on what kind of a tool you can use to, I mean, I don't know, I mean, for the human involvement, you want human to take more responsibility or make it less cumbersome for the humans. And so here that we have to develop some kind of a GUI, so you can directly click this point to pick and click this point to release. So somehow I remember they collect about a few hundred demonstrations probably. And so this will, I think the minimum amount of data you need to train some kind of deep models, deep neural networks. But yes, as I mentioned, so this is something that I probably cannot provide a general answer. It really depends on which specific task. And if there's an easy way to automate this, the way of you encoding this kind of human expertise. So yeah.
Because I guess one argument could be that there might be tasks that the human actually has no idea how to do, right? And that the robot, through its algorithms, whether they're learning algorithm or planning algorithm, might be able to gather knowledge that the human actually doesn't have. And I think in those cases, the kind of, yeah, like that approach of the robot learning by itself would make a lot of sense, because the human just doesn't have any input to give at all. And I wonder what these tasks would be. I don't know if those would be.
I mean, you definitely have those kind of AI systems that excel at the human skills, right? I mean, for now, like kind of, I think the Go system, human players cannot really understand what this kind of Go system are playing with. So, but wow, from the learning perspective, if we want to build some kind of system that's already somehow working, then probably you can start from something like, right, you are learning from the existing game, because it is there and it is not hard to enforce that. But yeah, as you mentioned, probably sometimes it's a kind of a human knowledge is not that immediate, it's not that straightforward to apply. But I don't know, maybe there is still a way to apply some kind of a, how to say that, common sense or something that's close to the task, which might not be strictly to the task. But yeah, this is something that probably are touching some kind of AGI or something like that.
Great, thanks.
Okay, anyone else has a question, please? We still have time, I think, for 1 or 2 questions. So,
okay. So will we upload this kind of slides or something like that? I don't know.
Yes, you can upload it. We can talk about that.
I'm asking, but yeah, I need to do that because I don't know. Probably I need to notify the other authors. And
of course.
One of them is not published yet. So, yeah.
Okay, sure. If no one has a question, I have a question. So, Hang, when you were talking about the state representation learning, right? And this has a bit to do with Rui's question about the structure in the latent space and what would happen if we had more discriminative factors to our data per se. So a lot of people have been working on this idea of trying to to give structure to these representations in a way that forces the creation of these semantically structured factors in the representation. So with these things about disentanglement and these beta VAEs and stuff like that. And I was wondering if during the execution of this work, did you have any sort of experiment with that? Did you play around with trying to see if the fact that we are trying to promote a latent space that might have this kind of structure, which is semantically meaningful, does it help in the planning of these tasks? It might completely blow your reconstruction capabilities of the model, right? But it might help to give some insight into exactly what the latent space is representing. And even though in the case that Rui was talking about the fact that we might have different colors, different shapes, whatever, maybe we can try to disentangle that. But I wanted to know your opinion on it.
Okay, I think this is a very good point, and because we also have a PhD students working on top of this, exactly this entanglement. I think for now, this entanglement, the problem is that we don't really have a very good tool, especially after that ICML best paper. It's kind of debunk many things that are, basically they have conveying something that you cannot get this entanglement for free or something like. You always need to incorporate some structure, and this is my naive understanding. But still, like you mentioned, those kind of a beta VAE, it still gives you something. And we did apply this to some toy data set, and also this actually. I mean, but this is just 2 days ago, so I don't know really what the significance of that. But at least on the toy data, we find that it's not that satisfying. Means that disentangled the dimensions are not really independent. Means that you always have some kind of correlations. So, but our idea is that, but you are right, I agree, this will indeed be helpful because somehow you can explore your state in a more like a meaningful way, because you know what will happen if you perturb, if you are moving along certain dimension, right? So if you know that, okay, so this is a kind of, I'm expecting a larger space and so a larger shape, so I supposed to perturb the second dimensions. So this will give you somehow a strong heuristics when you do this kind of search. So you are not just blindly search all of these kind of dimensions. So yes, so this is, but the thing here is that, and the thing here is that a lot of the kind of this entanglement needs kind of a label to give you a relatively strong result. So what we are thinking about is not have all full of the information, so not accessing the full labels, because I mean you cannot enumerate all of the factors, right? You cannot enumerate all of the lighting intensivity, the lighting, the texture, the material, the perspective. You have just have 2 factors. So probably again you can take a task perspective. You choose focusing on the factors that are matters in your task. And so in that sense, we believe there might be something that can be helpful here, but we are still not sure yet because it's just a kind of a separate line of research. People doing generative models are looking at this, and we see there's a potential to merge this together. But indeed, on this kind of data, and to answer one of your questions, that the reconstruction looks not compromised too much. I mean, from the standard of an VAE, right? VAE will not give you perfect reconstruction, but still fine. And also with some kind of normalizing models, it's even better. But that's we still don't know that's what does it mean to us for now. But indeed, there is a line of research going that, and we are interested in this direction as well.
Okay, thank you, Hank. So we have time for one final question, if someone wants to step in.
Oh, someone raised their hand.
Check. So say if you have a question, so if you want, just unmute yourself, go for it.
Hi, can you hear me?
Yes, perfectly.
Hi, my name is Saif. I'm a PhD student at the University of Birmingham. First of all, thank you very much for organizing this. It was a very interesting session, and thank you, Hank, for the talk. I just had a question about the variable impedance controller that you had. It wasn't clear to me what exactly you were learning in that part. Are you learning the impedance parameters in the controller, or?
Oops. Yes, I mean, you are right. I mean, you are also learning the parameters here, I think. Yeah, so you can see that it's just a different form of it's not neural network ties. I mean, so you are directly trying to learn this kind of parameters, and because of the stability constraints, it has to be in the other space, or let's say in the other space rather than the regular Euclidean one. So this poses you some kind of challenges, not to use the naive, I mean, or the most fundamental form of CM or other reinforcement algorithm.
Yes, I understand. So you're limiting the search space by looking only in the stable.
Only the stable one. And since you are only sampled from the stable one, so you'll be sure that all of your explorative actions are also stable. So this is a different, like you are having adding some kind of noise on your actions, then you don't explicitly say that although probably the mean behavior is stable, but you have no idea what's about it because it's completely stochastic.
Yes. So my question is, are you learning a constant parameters for executing the task, or do you learn a sequence of these?
Yes, you can also consider it as a kind of like how to say the multi-arm banded problem, because basically you are just deciding one type of one set of constant parameters here. But actually the controller itself is still state-dependent impedance controller. So because that's the part where it happens, you have this activations, which is depends on the and it's have a relatively complex form. You can refer to the original paper, but overall you can write it in a form like this, so you can still review the VIC structure, but overall the system is stable, and if you fulfill this kind of condition.
And you assume stability by assuming that the environment forces are constant, right?
No, I won't say that. It's basically to say the constant. It's just you are just need to assume that your environment is passive. Means that there's no energy injected to the entire system besides your robot actuators. So the contact force can be whatever it is, because to the robot these are modeled as perturbations. So of course, if you have a permanent perturbation, you will lose this asymptotic stable. You will never reach the target goal. But still, you have some kind of a bound about the energy of the entire system. Because if the environment is passive, the robot itself is definitely passive. It will never generate energy more than you inject to the system. So you can still say the entire system is somehow have some kind of safety.
Okay, yeah, I understand. Thank you.
Okay, we are out of time for questions, but I would just like to thank once again Hang for the presentation, for the time. It was great to see you again. And I would also like to thank everyone for coming. And before we go, I would just like to give a quick announcement. So Hang, can I share my screen, please?
Yes, please. Okay, I should stop, or I can.
You need to stop, yes, please. Okay, so just one final announcement exactly. So we have good news. So we are going to have our next session of Talking Robotics next week, and we're going to have the pleasure of having Professor Naomi Fitter with us, she's an assistant professor at the School of Mechanical, Industrial, and Manufacturing Engineering of Oregon State University, and she's going to talk to us about something really important, which is telepresence robots and telepresence, which I think it's a hot topic right now that we are all closed at home. I would sincerely invite you to check out her work and her Twitter, because she's been doing these amazing videos about how to do telepresence classes during quarantine. And she's also a stand-up comedian, so you know it's going to be funny, the presentation. And I hope to see you all next week, the 2nd of October, to check out the presentation by Professor Naomi Fitter. Okay. So with that, we close the session. So I hope you have enjoyed, and see you next week.